Good morning and welcome to our third session on evaporation. In the second session, we discussed the set of equations which can be used to undertake some calculations or even to design an evaporator. I would like you to check whether you are able to solve or to write down. If you are able to write down the total mass balance on your own, you should be able to write the material balance related to the solute, the energy balance on the solution, energy balance on the heating steam, as well as the heat transfer rate equation. Now, one of the fundamental questions that one has to answer or address when discussing evaporators is to find out the appropriate temperature at which um, evaporation should be conducted to be successful. What is the correct temperature at which your evaporator should be set to ensure that your solvent is evaporated? That question amounts to finding the temperature at which your mixture, which is supplied to your evaporator, is going to boil. So here, for you to determine the appropriate temperature of your evaporator, you have to determine the boiling point of the mixture. You'll bear in mind that the boiling point of a mixture is always higher than the boiling point of pure solvent. Now, to determine the boiling point of a mixture, which is the appropriate temperature for undertaking evaporation, we have three different options. You can use an equation of state with an appropriate mixing rule, referred to your thermodynamic uh, subject in S3 or S4. When you use an equation of state with an appropriate mixing rule, you are aiming for high accuracy, but you can also use for ideal solution, dilute solution, Raoult's law, such that the pressure is equal to mole fraction of the solvent in the liquid phase times the saturated vapor pressure of your solvent. And if you know the pressure at which your evaporation process has to take place, you can determine the saturation vapor pressure, and from the expression of saturated vapor pressure, you can determine the temperature. For concentrated solutions, you have to uh, take into account the activity coefficient of your solvent, which is water here. Refer again to your chemical thermodynamic subject to remind yourself of the concept of activity coefficient. Good news or bad news, I'm not quite sure. In this subject, in this, during the semester, we are going to use none of these. We are going to focus on the use of chart, the use of nomographs to determine the boiling point elevation or the boiling point of the mixture, which, remember, correspond to the appropriate temperature at which your evaporator should be set. Now, you have here what we call Turing chart. If you know the boiling point of your pure solvent and you know the composition of your mixture, the amount of solute that you have, you can determine the boiling point of your solution. That would be the temperature at which you have to set your evaporator. For example, you are working at atmospheric pressure, 100 kPa, and you are working with 40 mass percent of sodium hydroxide in water. How do you determine the boiling point of the mixture? Now, you check first of all with your steam table at atmospheric pressure, water boils, pure water would boil at 100 degrees Celsius, which is around 212 degree Fahrenheit. Following the vertical line to the horizontal axis, coming across 40 mass percent, there you can determine the boiling point of the mixture slightly above 250 degrees Celsius. A similar chart is given in our textbook, applicable to a wide range of solute. In the same manner as previously, you have to determine the boiling point of the pure component. For example, the boiling point of pure water at a certain pressure is 270 degree Fahrenheit. If your component dissolved in water is calcium chloride, and you know that pure water at the given pressure will boil at 270 degrees Celsius, you have to draw a line from that uh, temperature, that temperature, uh, instead of solution temperature, you it is better to say that it's the pure component temperature. So from 270 degrees Celsius point, you draw the line going through the point representing your component. You have the intersection with the left-hand side vertical line. From this intersection, knowing the composition, which is 22% of calcium chloride, you can draw the line which will give you the rise in boiling point, which is around 9.7 degree Fahrenheit. So to one and so on. So instead of using that weight percent solid uh, line, if you don't have enough space, if there is no means for you to have in an intersection here, you can also use that other one. Now we'll need the enthalpy of mixture when analyzing our evaporators. You see here we have the feed will be a mixture, as well as the product will be the mixture. To find the enthalpy of the mixture, you can refer to what we discussed while studying crystallization, but you'll always find a wide range of charts like this one, which was constructed for sodium hydroxide solutions. Once again, knowing the mass fraction, knowing the temperature, you can find the enthalpy of the system. An exercise: an aqueous solution of sodium hydroxide is evaporated at 6 psi A. If the solution is 35 weight% of sodium hydroxide, determine the boiling temperature of the solution, and B, boiling point elevation. Please don't answer C, don't determine the activity coefficient, as it's not part of our topic today. I'll give you the answer in the next clip. Thank you for listening. Bye.